Hi guys, welcome to the first lesson of the acid-base section of the curriculum. This lesson will just be a general introduction to and an overview of acid-base balance. In the second lesson, we'll talk about buffering responses to imbalances in pH, and then in the last lesson, we'll talk about the compensatory responses in some detail. But for right now, I just want to sort of start really simple and make sure everybody's in the same spot. And then we'll progress on and we'll do a general overview of the sort of acid-base system as we have it to this point. So, first of all, the definition of pH. The spot we always start with in these sorts of things is the negative log of the proton concentration. And you should notice that this is the free proton concentration or hydrogen ion concentration. I will use the terms interchangeably. This concentration of free ion is actually very small. So that makes it a little bit more convenient to measure it in log units, which is why we use pH to measure this. And we'll talk about why it's small in a second. So when we talk about a solution or the plasma, we say it has high acidity when it has a high free hydrogen ion concentration, which means it will have a low pH. High alkalinity means a low hydrogen ion concentration and a high pH, so they go in the opposite direction. And you will notice that this free hydrogen ion concentration is regulated to be within a fairly narrow range. The normal extracellular concentration is 40 nanomolar, that's 10 to the minus 9th. And the intracellular fluid concentration is normally about 100 nanomolar, again, 100 times 10 to the minus 9th. So this is pretty low. When we talk about millimolar, we're talking about 10 to the minus 3. We're talking about 6 orders of magnitude less than that. The upper limit compatible with life is 160 nanomolar. The lower limit is 20. So basically, we're talking about a pretty narrow range here. I shouldn't say compatible with life, but once you get below 6.8 or above 7.7, you're in serious trouble. So we're not talking about a big range of concentrations here that we have to keep our pH regulated within. All right. If that hydrogen ion concentration gets outside of that range, you're talking about a lot of serious issues. Issues with the central nervous system. Enzymes typically work optimally at optimal pHs, and if you drop out of that optimal pH range, you change the enzyme activity. Usually you decrease it, and that can be extremely hazardous. And we'll talk about this in the very last lesson more than anywhere, but potassium ion concentration tends to vary inversely with hydrogen ion concentration. So if you have alkalosis, you can have a hyperkalemia that will go with that. And if you have acidosis, you can have a hypokalemia that will go with that. And as you know, that causes some serious effects in excitable tissues, including the nervous tissue. So that can be a fairly dangerous side effect of letting the pH get outside of the optimal range. Acids and potentially acidic materials are constantly produced through metabolism. And so we can take acids and we can classify them into two categories. The first is carbonic acid. Carbonic acid is this H2CO3 molecule, and that is an intermediate in this reaction, which is arguably the most important reaction in physiology. When we talk about carbon dioxide, when we talk about bicarbonate, we're talking about molecules that are associated with our carbonic acid buffering system, okay? So they are a special class all on their own because they are the primary physiological buffers, and they also happen to be the molecules that we deal with for the most part when we talk about compensation, which I'll get to soon. We have non-carbonic acids, and these include sulfuric acid and phosphoric acid. Those are primarily found in the intracellular fluid. We have lactic acid, which is generated when you have hypoxemia because you can't operate your Krebs cycle. We have ketones that are generated in diabetes and starvation. These are all acids. The notation for a non-carbonic acid is HNC. That is the one I'll use the majority of the time. For H for acid, bound to NC, non-carbonic acid. Acid. So when you put an HNC, let's say hydrochloric acid, in solution, it associates into your hydrogen ion plus your NC anion, which in the case of hydrochloric acid would be chloride. Okay, so this is typical notation that we will use to represent non-carbonic acid acids in the equations that we're going to show. Another way that is typically used is NCA for non-carbonic acid. Okay, so get used to seeing this sort of equation. Sinks of these acids. First of all, if we're talking about an acid generated by metabolism, we are often talking about carbon dioxide here. The sink for carbon dioxide is the lungs. That is where you blow off carbon dioxide. So when you expire, you're expiring carbon dioxide. You're getting rid of the carbon dioxide that builds up through metabolism. For the fixed acids, phosphate and sulfate, you're talking about excretion to the kidneys. We've covered that, of course. We particularly covered phosphate as a titratable buffer, so that is the way that those are typically disposed of. Acid intermediates like lactic acid and ketones, again, are disposed of typically through metabolism, and then we have various other acids and bases that you might take in through the diet. And those are distributed through all these mechanisms, okay? They're disposed of through all these mechanisms, so those are your sinks. All right, let's cut it off there, and we'll start our next video with acid-base imbalances.